This talk is dedicated to flow management. And first of all, we must discuss the notion of flow. What is flow? Because actually flows are used in networks since very old times, and they are used in many cloud software. The flow itself appeared as a tool for network diagnostics more than 30 years ago. And only after that time, only after passing about 10 years, it was used for controlling routes information. And it's interesting that I don't know how the situation is in Thai language, but in Russian language, we have one word which corresponds to flow, to flux, to stream, and to current. But English language has separate words for each meaning, because flux is a quantity, a stream is something flow, and current is more like sequence of flowing in instances. Yes, but in some languages there is only one word which means everything, and this creates some inconveniences. The first time flow appeared as a part of NetFlow protocol, which was invented in Cisco in 1995. And they use it only for monitoring of network data. And it's interesting that they use the term traffic, which is actually somehow connected to road traffic, and you will see this connection later. They defined flow as packets having same 8 parameters, like source IP, destination IP, and 6 others. And this sequence of packets was named as a flow. And you can see overview of NetFlow capabilities if you follow this link. And as I told you, only 10 years later, these diagnostic tools has evolved into had evolved into a tool for routing and forwarding. And there is an interesting survey which was conducted in 2018. The author of the survey tries to understand what does it mean flow, and how this flow is connected to electrical circuits, how this flow is connected to our world. And I want to draw your attention to the figure above. You can see the road, and authors of this survey, they put this figure to demonstrate their article. And they authors made 6 attempts, after which they came to the definition of flow. So if you want to manage something, if you want to work with something, you have to name it and you have to define it. And there is a saying in England, name it to tame it. Yes, if you want to manage something, you have to name it. So we will try to define flow from 2 perspectives. First of all, we can study RFC. RFC is a request for comment. It's like a standard in network and IT world. But standards proposed by individuals, by companies, and so on. So it's not a very formal way. And we will try to define flow mathematically, because there is a rigorous mathematical definition for a flow. I found several RFC which give definition for flow. Several definitions were found from Wikipedia, and one definition was found occasionally. So you can see this 4 RFC which contain definitions for flow in networks. The first RFC 2722 defines flow as a portion of traffic delimited by a start and stop time. So flow is a transient value, so it lives only for a period of time. And it belongs to one of the metered traffic groups. So we have to define traffic group somehow. And what is traffic group is not defined in 2722. So we have to define traffic group, and there is no rigorous strict definition for traffic group. So while this definition is good, it lacks some important properties. There is a good definition in RFC 3697. A flow is a sequence of packets, or it's much closer, sent from a particular source to particular unicast destination, and which is labeled as a flow. So we see that it's actually a sequence of packets and which is sent from source and destination. So if we want to define a flow, we need notions of source and destination. And then there is the RFC 3917. And here they define flow as a set of IP packets which correlates with previous definition, passing an observation point. There is no observation point in previous definitions. In the network during a certain time interval. Okay, and this one correlates with the definition number 1 when we say that flow something that lives between start time and end time. So it's a transient entity. And finally, RFC 7011. Flow is defined as a set of packets of frames passing observation point. We've heard about this. In the network, we've heard about this during a certain time interval. So this is also known to us. And all packets belonging to a particular floor have a set of common properties, which is very similar to what was set in the definition number 1, and which is similar to the definition by Cisco NetFlow. Yes, they say that flow is a sequence of packets having common properties. And as they listed these common properties, source IP, destination IP, and so on and so on and so on. And we can unite different definitions to create some more rigorous and more clear definition of a flow. So it is a part of traffic or transmitted data with common traits, which are called source IP or traffic groups or something else, passing through an observation point. So there must be an observer. There must be someone who observes this traffic. For a finite period of time, we show transientness of a flow and between source and destination. This is a flow, a part of traffic with common traits, passing through observation point for a finite period of time and between source and destination. If there is no destination of source, it's not a flow. If it's not transient, it's not a flow. If there is no observation point, there is no observer, it is also not a flow. And it's always useful to use some analogies. And I try to understand how this title flow arouse, and why we use word traffic, which is usually used for road traffic, for vehicular traffic. And it looks like this term arose in 1950 during the establishment of the traffic theory, when several specialists from General Motors tried to simulate and understand how roads work in general, and how can we manage cars on roads. While this work started in 50s, in 1960s, this road traffic theory transformed into theory for flow networks, and that's how the term for flow arose. And you can see in brackets, you can see references. All references are at the end of my presentation, so you can follow this reference to read them. And there were two, actually, there were two ways to look at flows of cars on roads. One is microscopic, when each car is tracked, and one is macroscopic, when an ensembles of cars are tracked. And it's interesting that the second approach was developed by a great physician and mathematician, Mr. Lighthill, who is known for his works in computational aeroacoustics and computational fluid dynamics. But as far as I know, actually, neither first direction, neither second direction succeeded in prediction of cars' motion, because both approaches has some flaws and some disadvantages. And therefore, while people try to apply these approaches, for example, for modeling of crowds, there is a special branch of traffic engineering dedicated to traffic of crowds, which is used for modeling of cities. But looks like the most important thing is that all this theoretical work gave birth to ideas of flow in electrical circuits in computer networks. And this theory of flow networks was applied to computer networks in 90s. The first work, I think, is in the middle of 1990s, so 1995. Maybe I'm wrong, because I don't remember the year precisely. But modern works are listed in references 2830, and the first work, I think, the first work appears in 1994 by Hungarian scientist Szabay, who showed actually similarity between motion of cars and motion of packets. And this is a very interesting result, because actually similar phenomena are governed by the same equations and by the same laws, actually. And I think that's how definitions from car traffic came into definitions of packets traffic. And then his ideas was summarized and developed by Indian scientist Chaudhuri, who wrote with his colleagues a long book called Statistical Physics of Vehicular Traffic and Some Related Systems. And he showed that a range of phenomena are covered by the same equations. So actually, packets flows in computer networks, car flows, financial flows, people flows, molecular flows, any kind of flows can be described by the same notions, by the same equations, and by the same methods. It's very interesting. And with Chaudhuri, we come to rigorous mathematical definition of a flow. And flow is defined actually as a value or current, a number of vehicles or packets. It doesn't matter. Now we see that they are similar, crossing a detector site per unit time. And here we see correspondence with definition from some RFCs. So it's a transient value crossing detector size or observation point per unit time. And what is different in this mathematical and rigorous definition is introduction of the word number. So actually, flow is a number. And it is defined on the edge between a source and sink. So actually, it is defined on a graph. So each network can be represented as a graph. Each vertex can be regarded as a source or sink. And the value of flow is bounded by the throughput. This is a very important addition, because if you have a maximum throughput of some edge on your network graph, then flow cannot go from source to destination, because it will stuck. And the sum of incoming fluxes is equal to the sum of outgoing fluxes. If you remember basic physics and Kirchhoff's law or divergence theorem, you remember that there is a correspondence to them. Now I try to compare both points of views and create some single definition from standards and from theory of traffic. So flow as a packets count, and we will see this definition at the end of the lecture. I'm sorry, but I want to point out that there is a deep connection between this theory and statistical physics. So if someone has passion to strong theoretical background, you can refer to works number 9 and 29. And depending on the context and depending on 2 points of view, flow can be a packet count, so it's like a diagnostic tool. It can be a forwarding rule, it can be an edge on graph, or it can be a structure in database which is used to represent 3 previous items, 3 previous emanations of a flow. And recently, I've listened to one interesting lecture from a Russian network engineer. And when I listened to him, I realized that actually flows are, in some sense, it's not a rigorous analogy, it's not a straight analogy, but in some sense, flows can be thought as a MPLS. Because in MPLS, you take source IP, destination IP, you take UDP and something else, and you assign a number to all packets that has the same attributes. And all packets that have the same attributes, they follow the same route. And the same happens actually inside virtual routers or switchers. You take packets, you take their headers, and if there are headers that have, if there are headers that have the same attribute values, they follow the same route inside this router or inside this switcher. And in MPLS, this is like global flows, because this label conserves within the whole network. So there is some similarity between notion of flow and MPLS. In our SDN world, looks like flows appeared in a work conducted by authors of NOx, software-defined network controller. You can see this evolution of citations about their first work, and looks like this is the first paper, because they have 2,561 citations. So that's a lot. I can tell you that's a lot. And it's interesting that authors justify why they selected flow-based forwarding rule over packets-based or prefix-based. And they tell that if we define rules per packet, then if we have a granularity per packet, this would create too much CPU load. If we have forwarding rules per prefix, so if we define rules for forwarding using only source and destination IP, then this would be too coarse. We will not be able to manipulate our resources in networks accurately. And looks like the flows, the idea of flow is flexible enough at the one hand, and on the other hand, it doesn't consume too much CPU resources. So if you want to understand justification why flows were selected for SDN world, then you can refer to pioneering work like this one. And when flow started as when does flow begin as a forwarding tool? So allegedly that happens in 2003 when this gentleman proposed to use flows as a forwarding tool at the conference, the next generation of IP flow routing. And in 2009, he wrote a paper, A Radical New Router, which was published in IEEE Spectrum. And after that, flow came into network world as a forwarding tool. And in our vRouter forwarder, flows are used, I would say, at the end of pipeline, at the both ends of pipeline. When a packet, if you remember previous small talk, when packet arrives at the ingress interface, we take its header and we use it to decide what to do with the packet. And here flows are used to store this information. They store actually flows are used primarily to store what to do with packet, to store information about decision. But also flow tables are used at the end when packet egresses. I told you yesterday that there are two main regimes in which vRouter forwarder works. And we studied a little packet regime, packet mode, and actually the standard mode is flow-based mode, during which we decide what to do with packets and how to apply different security group and access control list. Packet mode allows us only to forward packets, and flows are used for security group, access control list, for net, for service chaining, and for other network functions which are needed. Therefore, you see that application range for flows is much broader than for packets-based forwarding. This is a figure which demonstrates in general how flow-based forwarding is applied in vRouter forwarder. I took this figure from Tungsten Fabric documentation, so you can find it on the internet. And you see that when, first of all, there is a difference between two states. In one state, we have packets coming from one virtual machine to another virtual machine, and both virtual machines reside on the one hypervisor. And there is another state when when each virtual machine resides on its own hypervisor. This figure corresponds to the case number one. When a packet arrives to ingress port, router forwarder takes its header, and it uses, it's written here that the router forwarder uses 5-tuple hash. This is wrong. Actually, it uses 6-tuple hash, including source IP, destination IP, source port, destination port, protocol, and VRF. Because let's imagine that you don't have VRF number, and you have tenants who have intersecting IP addresses. And in this case, if you have tenants with intersecting IP addresses ranges, there might be a situation when a flow from one tenant is applied to packets from another tenant, and you don't want to do this. Yes, that's why actually VRF ID is added to this tuple. It is added actually implicitly, so we can think of VRF ID, but actually we take not a VRF ID, we take a ingressing interface ID, but each ingressing interface ID is linked to VRF ID. Therefore, we can think of the parameter number 6 as an ID of VRF table. Therefore, when we have this 6 parameters tuple, we are looking up for flow. If we find this flow, then we take the decision for this packet. If the decision to drop, we discard this flow and we increase counters and so on. If the decision to forward or translate this packet, then we send this packet for next routines for another processing functions. And in OpenSDN, flow can be represented as a matching rule or flow key. So it's a rule which allows us to select packets. Then it's an action which is associated with selected packets: drop, mirror, forward, and so on. And actually, it is also called a state. So if you find flow state or flow action, these terms are interchangeable. And also flows holds additional information about source and destination, like MAC addresses, security group, virtual network names, quality of service, and many other. The key of a flow, which allows us to select packets, contains 6 numbers: source destination, source port, destination port, protocol, source IP, and destination address. Yes, six parameters. Well, and actually it can be a bit mask. So you can specify, for example, source port, but also you can say star instead of source port, and then this flow can be applied to all source ports. Or you can say source IP address specifying all bits, or you can specify only subnetwork, yes, and then this flow can be applied to all packets originating from some subnetwork. So you can think of this as a bit mask. OpenSDN forward denotes key, flow key, source destination interface using K and H. So each time when you type flow -L, you will see source IP, destination IP, and you will see K and H. And K and H corresponds to source or destination interface, which are used to distinguish flows from different tenants. And depending on a protocol, MPLS or VXLAN, depending on whether flow goes from one hypervisor to another, or flows starts and ends in one hypervisor. This KNH can be the same for forward flow and backward flow. We will talk about these types of flow a bit later, or they can be different. Therefore, you can use these hints to understand what kind of flow you see. Here are main states or actions of flows. You're familiar with drop, you're familiar with forward, and I hope you're familiar with network address translation. And there are two additional states or actions. Action hold. It means that a packet is put into buffer and waits for some condition. We will talk about hold action later. And mirror means that we must copy this packet. For example, we want to inspect a packets using some IPS system, and we don't want to consume CPU resource. We don't want to slow down connection. Yes, in this case, we create a copy of packets, and then we can analyze them separately on separate virtual machine or on separate CPU, while the original packet is processed as usually. And here is the most interesting part, which is missing in their documentation. So I recovered it from source code, from pieces of notes from different developers. Actually, OpenSDN has its own classification of flows. There is an ordinary flow, which totally correspond to our definition, which we made according to standards. So is a transient entity from source to destination, observed by someone, and so on and so on. This is an ordinary flow. But there is also fat flow. A fat flow is a flow where any parameter in its key is substituted with star. For example, when we spoke about this here, I told you that, for example, we can apply for a range of IP addresses or for a range of IP ports on UDP ports and so on. Therefore, when a flow is applied for a range of key values, then it is called a fat flow. And there is also a short flow. If you remember, we have a definition of flow of a sequence of packets coming from source to destination. And if our router cannot find this route, cannot find this edge between source and destination, then this is called short flow. And there are two types of flow. Forward flow is a flow which goes from source to destination, and reverse flow is a flow that goes from destination to forward, from destination to source, I'm sorry. Therefore, usually for communication, you always need two flows. If you send a packet from client to server, and it's expected that client receives an answer from the server, then you need two flows. Yes, you need a forward flow to send an inquiry, and you need a reverse flow to receive an answer. And as I told you, it's better to have some analogies in head. So first of all, flows have obvious analogy with rivers, yes, because rivers flow. If you consider small rivers, small tributaries like Nan, Pasak, then they are ordinary flow. They move ships from source to destination, one by one. If you consider large rivers like Chao Phraya, they unite river flow from different tributaries, and that's why they are fat flow. And if you put a dam preventing flow of water, so that ships cannot go downstream, you create a dam, and this is a short flow. That's how you can regard flows in networks. In OpenSDN networks, I'm not sure whether the same terminology is used in other controllers. But if you think about the ordinary flow, the analogy with river is absolutely correct. We can also introduce a notion of L3 flow, which is flow where any interface has INET type. When a packet uses L3 labels, when a packet uses L2 labels, but destination MAC is associated with L2 next hop, and for example, flows which are used for network address translation. So all these cases are listed on the slide. Now, what information is needed to organize flow forwarding? Well, actually, we need routes table, which links IP prefixes with next hops. Then we need next hops tables, because if we have links between prefix and a link between a prefix and the next hop, then we have to define a next hop itself. Of course, we need a flow table, and we need interfaces table, because interfaces ID are used as one of value of flow key. And we need functions to look up in flows. This information propagates via OpenSDN program in the next sequence. First, an operator or an orchestrator creates configuration inside config module. Then this information propagates to controller. Controller processes this information, creates routing information, local routing information base, sends it to the router. And we have the router split into the router agent. The router agent creates forwarding information base from routing information base and sends this information to the router forwarder. And the router forwarder creates its own flow tables, which are used for packets forwarding. But if you look at this figure, you will see that actually we see config, controller, and the router, which are physically separated. And actually, you now know that the router agent and the router forwarder are also physically separated. Therefore, information about flows is also separated between different modules. And we have a main flow table, which is finally used for forwarding of packets inside the router forwarder. And it's a hash table. And we have also some auxiliary tables, which are used for managing flows in the router forwarder. There is a flow table inside agent. There is a flow aging table and other tables. This is very important because when you analyze what's happening inside your network, you can monitor different tables. And the most problems comes from discrepancies between tables. For example, flow table in agent has an updated state, while flow table in the router forwarder somehow freezes. And this might create problems. The flow table of the router forwarder is allocated only once when agent asks the router forwarder about this. And some of you encountered this problem yesterday I remember that two of you who were doing tutorial encountered with this problem. They received error message on the first request, and this request corresponded to a situation when the router forwarder was not able to allocate memory for flow table. Even if you do not use flow regime, the flow table must be allocated. Then insertion and deletion of elements into this table is done by requests. Requests are formulated using XML language, and the router agent is responsible for formulating these requests using its own flow table. But actually, the router agent has two ways to interact with the forwarding table, which resides inside the router forwarder. It can send insertion or deletion request directly, but it can read this table using shared memory. We talked about ways how the router forwarder talks with outer world, and I told you that it has some auxiliary interfaces which are used to send information to the outer world. There is a netlink channel which is used to send or receive send request or receive response, and there is a shared memory which is allocated using a map Linux kernel call. What can we do with flows? First of all, we can install flow, so we can create it. Then we can update flow. We can evict. Eviction means it means that we destroy flow only in one direction. So we can selectively destroy forward flow or reverse flow without affecting another direction. And we can delete flow. It means that we destroy flows in both directions. So if you delete forward flow, the reverse flow will be deleted simultaneously. If you delete reverse flow, the forward flow will be deleted simultaneously. And flows can be analyzed. We can gather statistics from these flows. Flows are manipulated by the router agent, or you can manipulate flows manually using VR CLI utility. And those of you who have completed previous tutorial or who don't want to finalize previous tutorial can play with VR CLI utility today in order to study how flows are created or manipulated in the router forwarder. Here you can see a little more detailed explanation how flows are updated. Actually, we have a config which talks via controller with the router agent, and the router agent actually has OPA-DB tables. OPA means operative tables, which resides in random access memory instant tables. And information from these instant tables go into flow engine, and flow engine programs the router forwarder. The router forwarder uses netlink to send requests to the router forwarder, the router agent use netlink requests to send insertion or deletion requests. It takes responses from the router forwarder. It also uses shared memory, as I told you, to inspect table, just only for read access. And it also uses PKT0 interface to receive packets for analysis. And this is a basic scheme how it actually happens when we want to create a flow. So each time when a forwarder see unknown flow, so a packet arrives at forwarder, and forwarder takes this header and sees that there is no corresponding flow for this header. Then forwarder takes this packet and directs it to PKT0 interface. And agent listens to this PKT0 interface. When it receives this packet, it takes its header and looks up into its operative database. In its operative database, it searches for routes, for next hops, for interfaces, and if all information is gathered, it creates a flow. If there is no information, for example, there is no such route, then it creates a flow, for example, with action drop. And it says to forwarder that all these packets must be dropped. But we remember that flow actually is a transient entity, so it lives only for some period of time. This is an important part of the flow definition. And the idea of separation of vrouter into vrouter forwarder and vrouter agent roots from simple consideration that forwarding program must be as simple as possible to forward packets, to switch packets as fast as possible. And complicated logic must reside in less performant part. So vrouter agent is less performant part, and vrouter forwarder is more performant and is more loaded, more computationally loaded. Therefore, there is no flow aging mechanism inside vrouter forwarder. So vrouter forwarder don't know how to terminate flows in time. This decision is created in vrouter agent. It has a separate table which is called flow aging. The analogy with H is simple. So each flow has a burst time. We set H time, and when some flow reaches time which is below its maximum H, then vrouter agent sends request to vrouter forwarder to delete this flow. And here is an updated version of our diagram how both programs communicate with each other. So actually, forwarder sends unknown header to agent via PKT0. Agent, using its flow engine, talks to operative database, and when it creates a flow, it sends request back to forwarder to install this flow with drop or forward or any other action. And forwarder answers to agent with the ID of created flow, because both tables must be linked together, yes, and a link is established using index or position of a flow in hash table. And at the same time, agent periodically, regularly monitors the flow table in vrouter forwarder using shared memory and selects flows for deletion. Each time when a flow ages, so the age of a flow reaches predefined time, agent selectively sends a request to delete this flow from forwarder. But reality is even more complicated, because OpenSDN must simplify our life, and therefore SDN must monitor changes in the network. For example, we had a virtual machine which resided on one hypervisor, and then this virtual machine migrated to another hypervisor. Obviously, the information which is needed to create a flow, to create tunnel, changed. And therefore, we have to update this flow. For example, somebody updated access control list, or somebody updated bridge routes table, or anything else. All changes that came from config must have corresponding changes inside the router forwarder, and the router agent is responsible for updating this flow table in the router forwarder. So each time when there is a change in config, this change translates into agent. This change translates into change in operative database, and then this change go into flow engine, and via flow engine, this update goes inside the router forwarder. Well, unfortunately, the screen is not too large, but if we put all places, all components of the router forwarder and the router agent on a 2D region, we will see some kind of map, and we will see step number 0 when unknown packet arrives at the router forwarder. Then we have a arrow 1 when we send packet for analysis. Then we analyze this packet and we send a response with new flow parameters from agent to forwarder, and forwarder finalizes this interaction between two parts by sending ID address, ID, or it's actually a pointer, a pointer to place in hash table where this flow is stored. And now both parts knows that flow is installed, and they know the addresses of this flow in hash table. And if you are familiar with the TCP protocol, if some of you, or if you study TCP protocol in the future, you will find that actually this procedure has analogy with TCP triple handshake. There is a SYN request from client to server when we do TCP triple handshake, and there is a flow request from forwarder to agent. And then server, TCP server sends SYN plus ECK to a client, and agent sends reverse and forward and reverse flow to a forwarder. This is like SYN plus ECK. And finally, client must say to server about established connection. This is needed to receive sequence number. And we, in our vRoute agent, we also need to understand where this flow is installed, whether it was installed and where it was installed. And forwarder sends ECK, and it sends actually a pointer to the flow in hash table, and this is like ECK with a sequence number. So these procedures are equal. And despite I told you that the router forwarder doesn't interrupt flows in its own, it looks like there is one case when the router forwarder does this, is when it receives a packet with a TCP RST flag. Looks like in this case, the router forwarder can do this automatically without talking to the router agent. But I have to check this maybe again, but according to the source code, looks like the router forwarder can do this. But this is the only case when the router forwarder can interrupt flow without consultation with agent. And finally, a few words about flow establishment, call stack, and agent. So agent receives a packet. It takes its header, and then it analyzes its header. It analyzes, first of all, it tries to find a proper route. If route is found, it tries to analyze whether interfaces from both parts of routes are accessible. Yes, if we cannot, if there is no destination interface, then this is a short flow. So agent creates flow, even with forward rule, but it says short flow. And such packet is not, and the packet that corresponds to such flow are not forwarded inside the router forwarder. This is like a DEM. Then agent looks up for reverse flow. So if we receive request to create a forward flow, then we will need a reverse flow. If reverse flow is not found, then agent says, okay, forward, but short flow. And when forwarder installs short flow, and packets in this direction will be also blocked. And there are many other situations when the route agent can block flow, or it can modify decisions or parameters of the flow. And the final step is encoding. We have a special mechanism which creates a request from the route agent tables in the format which is acceptable by the router forwarder. This step is called encoding. And then we send information using SUNDASH requests. When you work with flows, you must understand that we have two separate parts, two separate programs. And in our case, one program resides in user space, and another program resides in kernel space. So they are managed differently. And actually, both programs are multi-threaded. The route agent is multi-threaded, and the router forwarder is also multi-threaded programs. If we speak about the router forwarder, an access to its elements or prevention of data race or other unwanted situation which happens during parallel execution, prevention is done by atomic flags. First of all, flow KLIN, and second, just flags. Okay, is an H entry flags. So anytime when a flow is updated in the router forwarder, it actually uses special atomic operation which tests and modify values simultaneously. You can look for the list of these operations or operators, for example, in GCC compiler manual. And the route agent is written in C++, and its prevention of data race or deadlocks is organized using well-known mutexes, semaphores, and other instruments, which are, of course, are very well known for every one of you. And we can analyze what's happening with flow management using two tables. We can analyze the router forwarder tables directly if we go inside OpenSDN tools container. Or we can analyze this table from the router agent by going into introspect API. And we must remember that the route agent actually provides proxy access to the router forwarder table, but it can also provide, it can also show us its flow table, flow agent flow table. Let's call it in this way. So flow table in vRouter forwarder is created from flow agent flow table. So vRouter agent provides us access to both of these tables. You can see examples of requests, how to see these tables. And you can enter these requests in your laboratory. Actually, there are other tools for monitoring flows, like tracing is a tool which is used to store debug messages in random access memory. We can use introspect. We discussed introspect previously. And well, and I think, and there is an interesting tool which is called flow filter request, but unfortunately there is no documentation for this tool, so somebody should study the code to understand how it works. But it's a very useful tool because it allows to filter flows according to some predefined criteria. Here are a list of comments which we use to which we use to read flows in OpenSDN tools container. Usually we use flow -l to show all flows, flow -get to show information about specific flow, and if you want to delete flow, if you want to evict flow, yes, you use command flow -i. And this is very interesting because if you evict flow from vRouter forwarder, this information will not be propagated to vRouter agent until vRouter agent deletes it using aging mechanism. So this tool flow doesn't affect vRouter agent tables. You must know about this. And a few words about hold, finally. If we look at this figure, for example, this figure, I told you that a packet arrives at interface PKT0. This is a known packet. But what should we do with the packet, with a known packet? There are several ways to process this packet. Of course, we can drop it, but what it means? It means that if someone connects to a virtual machine and first packet is dropped, then it means that connection will be somehow reset. And this is not acceptable. What developers of vRouter forwarder decided? They decided to create a small buffer associated with each flow. Each time when unknown flow arrives, they take a packet belonging to unknown flow and they put this packet in this buffer. And while vRouter, and then they send this packet, the header of this packet for analysis. While agent is analyzing this packet, its copy is stored inside buffer. However, this the size of this buffer is limited because if we make this buffer unlimited, then we can easily we can easily consume almost all memory. Yes, we can create a large bunch of flow of unknown packets, send it to forward, and this will consume all memory. Therefore, the size of this buffer is limited actually to 3 packets. So only 3 packets are stored. Therefore, if a client sends more than 3 packets, then fourth packet, fifth packet, and other are dropped if this packet are unknown. And you can control the length of this buffer using sysctl utility. The packet which await inside this buffer has a hold state. The flow has hold state, and the size of this buffer can be controlled using sysctl utility. Finally, what the final most, I think, important takeaway from this talk. Now we know that flow can be used as a diagnostic tool, and it was originally used as a diagnostic tool. It can be used as a forwarding tool, but it also can be used as a prediction, modeling, and research tool. And a flow in OpenSDN is a rule for forwarding and inspecting a part of traffic with some common traits, which pass through some given observation point during some time interval and between a source and a destination. Okay, and bibliography is attached to the presentation. I think you can download it. That's all. And we can go for lunch.
I didn't end up on your topic ไหมโอเค เช้าน่าจะหมดแล้วฮะ อันนี้น่าจะ ไม่รู้ว่าพอจะเข้าใจกันหรือเปล่านะ แต่ว่าพูดภาพรวมคือเรื่องของการ management flow ทั้งหมด เขาพยายามที่จะเล่าว่า flow มันเกิดขึ้นมาได้ยังไงเรื่องแรกหลักการของการทำ flow แล้วก็ชอบตัวอย่างนึงที่เขายกตัวอย่างเรื่องของ flow ที่เป็น flat flow กับ single flow นะที่เอาแม่น้ำหลายๆสายมารวมกันอันนั้นคือ flat flow แม่ไหลลงมาแม่น้ำปิงวังยมน่านไหลลงเจ้าพระยาคือ flat flow ไอ้ flow ที่มาเริ่มต้นจากสายเดียวคือ single flow คือ flow เดียวแต่ความหมายของเขาคือ flow ที่เกิดขึ้นเนี่ยมีไปกับมี ingate โฟที่เกิดขึ้นถ้าเกิดมีแค่ข้างเดียวไม่ครบโฟแสดงว่า connection ไม่ได้ต้องมีโฟขาไปและโฟขากลับโฟขาไปก็คือโฟที่ create ขึ้นมาจาก initial จาก client to server ขากลับจากเซิร์ฟเวอร์กลับมามันก็คือ reverse flow นะฮะแล้วก็ส่วนข้างหลังที่เขาพูดมามันก็คือเรื่องของการดิฟลงไปในหลักการในการ develop ซึ่งมันก็เป็นเรื่องของโค้ดละไอ้ที่บอกว่าflow entry อันนั้นคือคลาสหนึ่งของโค้ดเบสที่เอาไว้เก็บแล้วก็โอเวอร์เลย์เรื่องของแต่ละคลาสอันนี้ก็จะเซสชันเช้าก็น่าจะประมาณนี้เดี๋ยวเรามาต่อกันเซสชันบ่ายอันนี้เซสชันบ่ายก็จะมีเลคเชอร์แล้วก็ทิวตอเรียลเป็นแลบโอเคครับจบสรุปย่อๆมานี้ครับพักทานข้าวครับ
This would be a rather long and tedious lecture. I prepared it for the first time, and therefore there might be some inconsistencies in slides, and material might sound too complicated. But even if you understand 10% or 20%, that should be okay, and I think it would be useful. Well, we have talked that while low-level details are boring, but they are like a multiplication table. So nobody likes to learn multiplication table, but everybody use multiplication table later. And if something was not clear to you, then probably it is not clear for me. The overall plan of the lecture is presented here. So we will talk about classification of SDN programs and SDN controllers. We will talk about main OpenSDN components and OpenSDN roles. How can you imagine OpenSDN? Which languages are used for OpenSDN implementation. And then we walk from layer by layer through main OpenSDN components and which basic principles are used for their implementations. We will talk about roots propagation, about used protocols, and I will finalize the lecture with a small guide how to download developer environment and how to upload your changes to Gerrit if you decide for example, to fix some bugs or to introduce some features into OpenSDN. First of all, why architecture is needed? Because every day we hear about architecture, but what is architecture? It is a logically connected compound of verified technical decisions, and it is needed to meet some requirements. Actually, requirements go before architecture appears. We have functional requirements from network virtualization, switch and router virtualization, and from network NFV. And we have functional properties and indicators such as scalability, performance, user friendliness. Some properties cannot be specified using numbers, and some properties can be specified using numbers. For example, scalability or performance can be estimated in throughput, in parallel quality, and so on. And when we have these numbers, when we have some predicates, we can formulate a requirement, and from this requirement arise an architecture of a program, or SDN program. Second question which is important is the difference between SDN and SDN controller. SDN is a large solution which usually includes SDN controller and virtual switcher or virtual router and network function virtualization applications and many other stuff. SDN controller is a tool which is used to manipulate routes, configuration of virtual networks, but many authors use them interchangeably. So, and we will do this during this lecture, but actually, if you want to be strict, then you have to separate these two terms. Let's talk about main properties of SDN controller. They are scalability, an ability to increase number of resources horizontally, consistency, an ability to keep tables in parallel computations in a consistent state, so they equal or they match each other if we keep tables separated or sharded, for example, like let's remember the example provided by Olga yesterday. She provided example of database sharding, and when we shard our database, we have to keep it in a consistent state somehow. Reliability and security. Reliability is a property to withstand some problems with hardware, with software bugs, and security is a property to conserve some security issues. And on this side, on this slide, you can see several works which introduce these key properties, introduce definitions for these properties, and assesses these properties for different SDN controllers. We discussed these properties previously, so I think we can keep this slide. And which types of SDN controllers do we know? Usually we classify SDN controllers as centralized, distributed, and hybrid. Centralized means that all information and processing of this information is concentrated on one computing node. Distributed means that we distribute information or processing of information on different nodes, and hybrid means that we mix somehow both approaches. Well, problems and benefits of both first approaches are known. So when we have a centralized SDN controller, it is, for example, NOx. It is convenience for small enterprises, for campus networks. It's wrongly mentioned here that it has problem with reliability. No, it's probably it's consistent. It doesn't have problems with consistency because there is no data sharding, no data partitioning, but it has problem with scalability, reliability, and perhaps with security. And on the other side, there is a distributed approach when questions of scalability and reliability are resolved, but we also face with large consistency problems, because now we have to synchronize our data. We have to synchronize calculations, and it is all a field of parallel programming, and we encounter regularly data races and deadlocks. And distributed controllers actually fall into two large groups, both logically and physically distributed. It means that we distribute some system logically between computational nodes and physically. And logically centralized and physically distributed means that we think of a control or a program as a logically centralized, but distributed physically. So different part can reside on different compute nodes, but they act as if they are the one program. Modern landscape of SDN controllers is actually very diverse. And I just mentioned several solutions, but you can find, my opinion, you can find dozens of them, maybe 50 or even more. But the well-known OpenSDN, Tungsten Fabric, Open Contrail, OVN, OVS, Open Daylight, RunSDN, Nox, one of the first SDN controllers. So if you want to understand, if you want to study how controllers emerged, and if you want to study first works about SDN controllers, then you can study Nox/POX, RU and others. OpenSDN is a physically distributed and logically centralized controller. It can be thought as a hybrid because it still can program Juniper devices, but I don't think that this capability will stay in the future. So probably the second line can be removed. And it is more than a controller. It is a platform, because it includes virtual switch, it includes virtual network functions, and it includes diagnostic tools. So it's actually a platform. It uses flow-based granularity, and just recently we have studied why flow-based granularity can be selected by authors, because it provides flexible management of packets while saving computational resources. It allows extension of control logic back to compute nodes, It allows to speed up request for flow. And it delegates state storage management of state information to external data store, namely Cassandra database, which is a key value database. And it was interesting for me to know yesterday that actually soon it might become a vector database. Globally, OpenSDN architecture includes 4 components. And I think during these 3 days, these 4 words were instilled and imprinted in your mind totally. So these components are distributed via 3 planes: management plane, control, and data plane. Management is responsible for global configuration of network. Control plane sends information, and data plane forwards packets. And what makes OpenSDN unique is its closed management cycle. Nowadays, almost all, even I can say all controllers or SDN can forward packets, they can route packets, they can create routes, they can create BGP sessions. However, there is a problem which persists until the present day. First of all, even if we talk about such a uniform program as OpenSDN, a lot of different languages, standards, and protocols are used. So they must be glued and connected somehow. Second problem is about SDN nature, because if we look at this figure, we see that there is a management plane, and we create configuration in language or in alphabet of management plane. And then this configuration is translated into virtual network configuration stored in control plane, and then this information is translated in language or alphabet of data plane. And when we have problems in network, we see diagnostics formulated in language of data plane. And therefore, we must create reverse projection in our mind from problems in data plane to actual configuration in management plane. And actually, this creates a lot of difficulties for network engineers, for developers, and for everyone, because information translates automatically from management plane to data plane. But when we want to understand what to change in management plane to fix problem in data plane, we have to create this projection or translation manually in our heads. And authors of Open Contrail, and now this is OpenSDN, they proposed so-called analytics component, which addresses this issue, which tries to find how problems in data plane can be mitigated by changes in configuration, how they are related. So this closed coupled management cycle might be a solution to problems. And the problem also is also in our nature, because you cannot keep simultaneously more than 7 words. So 7 plus minus 2 words can be in your memory simultaneously. Therefore, all this hard work must be offloaded to computer as much as possible. On the management plane, we have analytics, we have all databases, we have analytics component, web user interface, config, and config database. And this plane manages virtual network configuration on high level, analyzes current state of virtual network, and provides user interfaces for the management of networks. On the control plane, we manage low-level configuration of our virtual network, and we manage routes, creating input information for forwarding plane or for data plane. And finally, on the data plane, we have our vRouter, and which consists of vRouter forwarder and vRouter agent. And our data plane is responsible for applying politics and applying forwarding rules to packets. As you see, we have 3 layers, 5 components, dozen applications, and there is a question how to implement all this complexity. Well, all of this is implemented using different codes. So graphical user interface is implemented using JS. Python is used for management plane, for config, for input data management, C++ for operative database management, C for packets forwarding, and so on. And we also need some kind of gluing technology, which is called interface definition language. Here we use Apache Swift version, which is called Sandesh. And we also use C and C++ for different purposes. C is used for performance critical parts of the code, only for data plane and for forwarding. And C++ is used for logically complicated parts of code like controller, vRouter agent, and virtual DNS server. As you know, different languages provide different advantages, and usually we can build such a hierarchy or ladder where we have assembler language at the lowest level, and this level provides us highest performance and memory and best memory usage. And at the upper level, we have such languages as Python or Java. Usually, the closer language to hardware, the higher its performance. But this also increases risk of errors and severity of consequences. So, as you know, it's very easy to ruin program or computation if you have a code on C or C++, and programs on Python or in some domain-specific languages are easier to use, but they have some performance problems. Languages can be also divided by using next approach. So there might be machine code, sequences of zeros and ones, assembler, which is actually mnemonics for binary code. So assembler is very close to binary code, and that's why it's very efficient. Then go general purpose code programming languages like C, C++, Fortran. Then go interpreters, which don't need translation into object code. And there is a specific domain-specific languages like LaTeX. If you ever saw scientific papers or serious journal papers, they are usually prepared using such languages as LaTeX. And I also gave as an example language Relap 5, which is used for nuclear energy management. And also languages can be separated into declarative and imperative. Within imperative languages, we specify steps we need to do in order to achieve some goal. And within declarative languages like Prolog, Lisp, we specify which results we need, and then program gives us results according to its internal rules. And you might ask yourself, why am I dedicate so many time to classification of languages? Because of the next. Because OpenSDN can be thought of different roles. You might have seen this figure, yes, if you project light on a cylinder, and you can see a circle on one wall, you can see square on different wall, but actually this is a cylinder. And the same for many things in life. You can think of OpenSDN as a compiler, and it is a compiler. It is a language. You can think of OpenSDN as a network system, operating system, and a virtual router. And thanks for great presentation, dear, where you explained in details how OpenSDN works as a virtual router, because it really adds a lot to this talk. And these roles can be also considered as levels, and we will see how this how this implemented actually. If you look into Contrail Architecture Guide, CHAP, you will see a chapter, Scale Out Architecture and High Availability. And their authors consider OpenSDN as a compiler that compiles high-level data model into the low-level one. Well, first of all, I think it's more interpreter, because there is no translation into object code. But if authors call it compiler, we will call it compiler. And usually each compiler has several steps like pre-processing, translation to object code, and linking. And our OpenSDN compiler also has its own stages. It has a stage of translation from high level to low level model, and it has a stage of translation from level model to low level model to forwarding information base, which is used actually for forwarding packets. And yesterday we saw that actually the router forwarder acts like a processor. Yes, it has several tables, and it processes these tables in some kind of fetch and execute cycle. And high level and low level model are actually just a language definitions. So they are not an actual state. And when we speak about actual state, then configuration state corresponds to high level model, and operative state corresponds to low level model. If some of you studied, for example, object-oriented languages, you know that there are classes and there are instances. So data model is a class, and state is an instance. And now we can describe our OpenSDN as a language. It's a declarative programming language, obviously, because we do not specify algorithms how to process packets. We only specify what we want to see. We specify configuration of network, we specify policies, so it's a declarative language. I call him interpreter, but authors call it compiler. And it provides instruments to define virtual networks. So it is a domain-specific language. This language is needed only for network, for creation of virtual network. And it provides virtual switches, and it has tools for failures diagnostics. But actually, OpenSDN is a network operating system too. It provides interface to modify network, to manage network, to distribute resources, to manage security, to manage authorization and identification. And the first notion of a network operating system was introduced in the work dedicated to NOx controller. That's why I paid attention to this publication in the previous lecture and at the start of this lecture. So if you want to understand the very first principles which were used to create first network operating system, which was to derive the idea of network operating system, you should refer to this work. This is a pioneering work. Or you can make a shortcut, open Gigs for Gigs, and they also give a great description, list of functions for network operating system, creation and management of user accounts on the network, controlling access to resources on the network, communication services between devices network, troubleshooting, configuring and managing resources on the network. It is all what OpenSDN does. Therefore, it is network operating system. Looks like a duck, works like a duck, and then it's probably a duck. And finally, OpenSDN is a virtual router because it allows us to manage routes, L2, L3. It can pair with BGP peers, with other BGP routers, and it can forward packets. So it's a virtual router on top of network operating system. Now, when we learned how to look at OpenSDN from different points of view, we can study how data flows inside OpenSDN. And actually, there are three streams of data. And we remember that flow, we use flow for a different entity, therefore I use stream. That's why English is good, because it has many words for similar senses. So there is a packets data stream, routes data stream, and configuration data stream. Packet stream is just a packet that goes from one interface to another and goes between hypervisors, and we manage how these packets go from interface to interface. The routes data stream is the information which programs how these routes, how packet streams are organized. This information propagates from controllers to vRouter agent, and then from vRouter agent it propagates to vRouter forwarders. And we see that controller is physically distributed, so we can have several controllers, but controller is logically centralized. So any vRouter agent connected to two of controllers actually think of these controllers as a single entity. And vRouter agents are physically distributed and totally physically distributed, so they are not centralized. And finally, there is a configuration data stream which programs routes data stream. This data stream starts at REST requests, then it propagates to config and database component, and then it propagates in the direction similar to direction which is applied to roots data stream. And I tried to put roles of OpenSDN and streams on one plane. You see roles on the horizontal coordinate, and you see planes on vertical coordinate. And we see that we occupy lower triangle. So usually we have a configuration, compiler processes this configuration, then data stream flows flows, and the role of OpenSDN switches. It becomes operating system because it distributes this configuration to other devices, virtual or physical. Then our configuration becomes routing information or data stream, and roles switches together. So OpenSDN becomes virtual router on all three for all three streams of data. And the rest of the lecture will be dedicated to questions how all these components, roles are implemented, how packets are forwarded, and so on, and how different parts are linked together. Everything starts with REST messages, which are used to program a high-level data model. REST messages can be of different types, like create, read, update, delete, and link. And these REST messages have specific structure, which is governed by some standards. You can find standards for REST protocol. And we can specify REST request using curl or using web user interface. So actually, when you hit the button in user interface, actually each changes in user interface are translated into REST requests. Requests are stored into two databases. First, they are stored in persistent database, which is called Cassandra. Cassandra is known to be used in, for example, in Netflix and Instagram. That's why their icons are here. And after translation of this information from persistent database into operative database, and we know now that OpenSDN acts as a compiler to translate this request. They are stored into operative storage, which is actually a collection of tables inside memory. Translation happens inside logically monolithic applications such as controller, DNS server, config API. I think we can skip this slide, or maybe just a couple of words. So Cassandra stores value in a key value approach. So actually we have two tables. One table has a mapping between type of element, type of network entity, and its identifier. And second table actually stores mapping between identifier and element property. Then this information, the information from Cassandra, is translated into ifmap database. Ifmap format is also governed by standard that was produced by Trusted Computing Group. I suppose this group is joint team of several companies because I saw names from Juniper, from Cisco, and other networking companies as authors of documents. And this IFMAP database is represented actually as a graph where objects correspond to entities of virtual networks and references between these objects are represented as edges. And finally, this IFMAP database is transferred into operative database, and which consists of tables. Tables are partitioned along CPU cores. So it's a different approach to sharding. Yesterday, Olga about sharding, which partitions computational efforts among different compute nodes. And in pure partition without sharding, we split computational efforts among different CPU cores using, for example, multi-threading libraries. Each partition contains entries actually as a tree, and each entry has several states. IFMAP database is represented like a graph, so it allows us different approach to cross it. For example, we can cross it using BFS, breadth, breadth, I forgot English word, proper English word. So we can go in depth and we can go in breadth. But how it is translated in English properly, I don't remember. And there are at least 5 applications of graphs in OpenSDN, and we will see how they apply it right now. First of all, graphs are used to specify data model. Data model graph is a central idea which is used in OpenSDN actually. It's a directed acyclic graph, a kind of polytree, which has a single root and several children. And references between nodes can be of 2 types. So you can see edges with solid lines and with dotted lines. Solid lines are edges for members, and references which say that they just know about each other. References is a second type of edges. And here is a simplified version, and I tried to display a full version of data model. It is much more complicated, and as you can see, it is even doesn't fit onto screen. And if you want to watch, if you want to watch objects, states created from data model, you can use introspect, for example, in user interface, where you can open each table one by one. Then our controller and also vRoute agent has their own small graphs, which are hard-coded into their code, and they used to cut configuration or to cut trees, and also they are used to propagate configuration information. I want to give an example. What does it mean, propagation of configuration? It means that, for example, if For example, if interface is changed, then we must decide which elements must be updated if one element is changed. And this task is solved using configuration propagation graph. And another task is creation of graph cuts. When controller receives when controller receives this full graph from config, it must decide which part of this graph must be sent to the router agent on a specific hypervisor. And we have a special list or special policy, which is actually represented as a graph, which decides which elements are sent to specific the router agent. For example, a polyforest of graph of configuration propagation graph. Also, red-black trees extensively used for storing information like routing information base, if map tables, and many other data is stored using red-black trees. Patricia trees are also frequently used for iNet unicast routes. It's obvious because radix 3 are good for storing prefixes. And finally, state machines are also graphs, and they are represented using a very interesting C++ semantic based on templates. We will not consider this today because it's an additional topic. But nevertheless, they are used to represent these graphs. And this is an example of BGP session state machine. And this is an example of XMPP session machine, which I extracted from the source code. And controller can be regarded as the central point for routing information base because it sends portion of its tables to the route agents. And it works as a pipeline. So it receives some kind of information, it processes this information, and then it distributes this information with its peers. And we remember that peers of controller can be of three types. The router agent are peers of controller. In other controllers, because we remember that controller is a physically distributed entity. Each controller instance shares its information with other controllers to have all tables consistent, to have all tables equal on each controller node. And controllers actually interact with other BGP routers from other networks, from other data centers, and so on. For example, you can see that each controller instance is connected with other controller instances, and it is connected with other config instances. So config is looks like logically centralized, but it is distributed. And finally, you can see here the pipeline for processing of route information in controller. So for this pipeline corresponds to data obtained from the route agent. So when the route agent sends information to controller, it is processed in step 1. Then this information is submitted into table. Information is inserted into table. Then there are special classes which creates aggregated version of information from several tables on one instance. And then there are special classes on steps 5 and 6, which are responsible for sending this information to all peers which might be interested in this information. Main parts of the router agent are ifmap database. So like a controller, it has a ifmap database. It has operative database. It also has a bunch of servers and proxy servers like metadata proxy, introspect, and so on. And it also has parts associated with the router forwarder synchronization. Main elements of routing information base is virtual network, is an entity which specify policies. Then goes virtual routing and forwarding, is a member which specify how to route and forward. Within this VRF, we can have several route tables, and each route tables have several routes, and each route has a prefix, is a address, as a destination address where we want to get, and each prefix can be L3 or L2. And each route, in addition to prefix, has a path consisted of next hop and peer. Peer actually is the origin. This is a very strange definition because peer means origin. If you look into the route agent tables, you will see that some routes, for example, have peer local VM port. It means that this route or this path has been generated locally on this hypervisor. Or you can see peer external, and it is called BGP peer, and it means that this path was created somewhere else and it was transmitted via, for example, BGP protocol. So actually, when you see peer in the route agent routes, you should know that actually it is a source of this route. It denotes who created this path. And you can see here how tables are actually distributed among several hypervisors. For example, let's imagine that we have two controllers and we have three hypervisors. Then we have orange, green, and violet hypervisors. And each hypervisor has its own agent, has its own router forwarder. And it means that, for example, we have 4 virtual machines on orange hypervisor. It means that each virtual machine will create its own root records, and they will be inserted into agent routing information base. And agent will send this part of its table to controller. And you can see that this part of agent routing information base is transferred to controller table. And the same applies to other hypervisors. This part of green hypervisor translates to middle part of controller tables, and this part of violet hypervisor routing information base transforms to controller. And then controller, when controller gathered all information, it reflects this information back to other hypervisors. That's how other hypervisors know about routes to their neighbors. So this part of green hypervisor on controller is transferred back to agent and is transferred back to agent, to violet agent. And for example, this part of violet hypervisor RIP is transferred from controller to the table on orange hypervisor and to the table on green hypervisor. Finally, there is one important mechanism which is used in OpenSDN, and it is called routes leaking. This process or procedure is responsible for exchange of data between tables. So when we have two tables and one line or one record from table 1 is copied to the table number 2, this process is called routes leaking. So even though it might sound mysterious, actually it's just a process of copying entries between two tables. And here is just an example. For instance, we can copy a record from table 1 and from table 2 into table 3, and it means that routes from table 1 and table 2 are leaked into table 3. And many components of OpenSDN uses this mechanism. For example, VXLAN control plane implementation uses routes leaking. VXLAN as a standard involves two parts, actually, data plane and control plane. As a data plane, VXLAN is about adding one more external header, and as a control plane, VXLAN is about redistributing routes to different VTEPs. And the default mechanism of routes redistributing is called flood and learn, and it requires a lot of resources from virtual networks. Instead, authors of Contrail and now OpenSDN decided to use some kind of central authority or PGP approach when we redistribute these routes centrally using controller. And this is actually we redistribute this, we copy routes or we leak routes on the router agent, but then these leaked routes are gathered in controller. But the principal idea is simple. We copy routes from one table to another. Example is shown here. For example, we have several networks with each VRF table connected to one VXLAN router, and it means that we have a fourth table to which we copy routes from each of these connected bridge virtual networks. Finally, when we have routing information based on our vRouter agent, we copy this information as a forwarding base into vRouter forwarder. And those of you who reached this figure yesterday might remember it because it depicts main parts of forwarding information base in vRouter forwarder. So forwarding rules are stored in inet routes table and bridge routes table. These tables reference next hop tables, and they are also associated with interfaces tables, which are associated with VRF tables. So each interface can belong only to one virtual routing and forwarding, or can belong to one virtual network. And as I told you, OpenSDN is a network operating system, and it provides services for application of high level. For example, there is a VDNS service, which is actually a separate application that runs on top of OpenSDN, and it uses Cassandra database for its own purposes, and it also talks with other OpenSDN services like vRouter and virtual machines. And all these elements are glued using a single interface definition language, which is called Sandesh. And Sandesh is just an extension of Apache Swift. It has two main goals. First goal, creation of single interfaces for different languages, because if we have some part written in Python, some part in C, some part in C++, we need some tool to synchronize interfaces between different languages. And Apache Swift do this work for us. And second goal is a standard or protocol for data exchange between different components. If you want to understand how to work with Apache Swift or how the process is organized, you can refer to the tutorial mentioned in this link. Basically, it is also a kind of layered library where you select how to transport data, how to encode data, and socket type is how to identify pairs of communication. And here is an example of interface definition. For example, we have a structure work. It has 4 fields. And after parsing this interface definition, we will have separate interfaces or interface classes or definitions in all languages, which will enforce types specified in this IDL. So we will have, for example, if we want to have 32-bit integer for num1, then Apache Swift will enforce this type of field for all languages we use in our components. While Apache Swift is relatively mature and old library, it also has rivals or replacements. So actually, it can be replaced by other ideal or RPC programs like CAP and Proto and others. Sandesh extends Apache Swift language, and it adds additional functionality. Additional functionality allows us to inspect state of our SDN controller, SDN vRouter agent in different ways. For example, there are UVE, user visible entities, tracing, and logs. UVE is a state which is polled regularly from different components. So we can poll components and ask about their state. Tracing is actually a ring buffer where we store log information. So if we want to debug a program or if we want to look about some intermediate results, we can save these results into ring buffer and extract them using tracing. And logs are simply logs which are stored on persistent storage like hard disk. And here you can see these types. They correspond to trace object corresponds to trace. UV is not presented here, but there is a UV type which corresponds to UV inspection and so on. And since SunDash is used for gathering information, there must be someone who generates information, generator, and there must be a collector, someone who collects information and someone who gives this information to us. Therefore, all applications in OpenSDN can be generator or a collector. And if you want to understand how to inspect applications of OpenSDN, you can look into its source code. There is a file vns.sundash, and this file contains ports for all services provided by Sundash. Finally, our OpenSDN uses external libraries. It uses Apache Swift for Sundash. We discussed it just recently. It also uses Intel TBB for trading management. It uses Boost library for memory management, for strings, yes, for memory, for strings. It uses for Boost, for example, for specification of state machines using graphs and for many other tasks. Also, bind9 DNS server is used. Scones tool is used for managing source code. And DPDK library is used to accelerate package switching. We use about 10 protocols and formats to exchange data. So main standards which are used in OpenSDN are REST, IFMap, BGP, Netlink for communication between agent and forwarder. Shared memory is used. JSON format is frequently used, XMPP, BGP format, Sundash, and XML. The code in OpenSDN it is tested mainly using J tests. First of all, this all concerns controller and VRoute agent, but other part might also use G-test. And for VRoute forwarder, there are self-written PyTests, which were written partially by Pragmatic Lab and partially by Juniper. Main repositories of OpenSDN are community, where you can find exhaustive list with description of each repository, docs containing documentation, but it is somehow outdated, so it really needs more work to finalize it. And VRoute and controller repositories contain information, contain source code for VRoute and controller components. And if we speak about numbers, OpenSDN source code counts about 800,000 lines of C++, 350,000 of Go, about 300,000 of Python code, and about 70,000 lines of C code. And if we add all of it together, and if we decide that someone produces about 70 lines of code per day, this is actually a good performance, because coding is not just a typing. It is also about debugging. It's about testing, checking. We can achieve that this program can be written in 92 work a year. So if we if we gather 100 coders, developers, and if we put them into one room, they probably will finalize it in 1 year. But if we gather them, there is a special container which is used to prepare this complicated development environment. This container is called tf-dev sandbox, and it is stored in repository tf-dev-env. It definitely works on Rocky 9.5. It definitely works now on Ubuntu 22. I checked this just a week ago. And well, it has a relatively relatively fresh documentation, so you can open readme.md and follow steps to run this container. But since it compiles 1.5 million lines of code, this will take about night on notebook. Yeah. If you have 4 CPU cores. If you have 16 or 32 CPU cores, this will take several hours only. Main stages are listed on the slide, and they are also listed on README. Finally, if someday you decided to contribute a project, there is a guideline. There is, or somebody in your family decided to contribute to the project. There is a contribution guideline which involves several major steps. First, you have to log in to GitHub, and you must create a public profile with public email on this profile. So email must be visible to everyone. Then you must install Git on your system and obtain SSH key. And then you can link your JRED account with GitHub account and install Git review on your local machine. And probably this is all. What's minute?
Have a question มีไหม มีไหมฝั่งนู้น มีคำถามไหมฮะ ไม่มีอ่ะโอเคฮะ โอเค โอเคฮะ ก็เดี๋ยวเบรกกัน10 นาที15 นาที แล้วเดี๋ยวกลับมาทำติวโตเรียลกันต่อครับฮะ
These tutorials use the same base. There is no need to recreate virtual machines again. And all steps are written here. And it looks like maybe it will be more efficient for us to try to try this tutorial in a different manner. You will follow steps from browser. And if you have any questions, you just ask me and I will help you. So you can select any of this tutorial, and if you have questions, just ask me.